The RRC protocol is responsible for managing the radio interface. The UE can be in one of two RRC states. The actions taken by the UE will depend on the state it is in. In RRC idle state, the UE will listen for system information, listening for paging, perform sales selection based on results from measurements, and, if the new cell belongs to a new tracking area, the UE will perform a tracking area update. Hence, UE location is known on tracking area level. If the UE is in RRC connected state, the UE will still listen for updated system information. It will also listen for scheduling grants, both for uplink and downlink data services. However, the UE may be configured for discontinuous repetition, DRX, and will then follow a specified sleep mode, configured by RRC in the eNode B. The UE will send measurement reports to the eNode B, and it is the eNode B that takes the decision for handover. The UE location is known on cell level. Depending on the activity, the UE will move between the two RRC states, the RRC idle state through the RRC connected state. When going from the RRC idle state to the RRC connected state, an RRC connection established procedure is used, and to change back from RRC connected to RRC idle state, the RRC connection release procedure is used. To exchange RRC signaling messages between the UE and the eNode B, signaling radio bearers are used. The signaling radio bearers are defined between RRC and PDCP protocol layers. Any NAS messages to be exchanged between the UE and the MME will be carried in RRC messages. Signaling radio bearer 0 is only used to establish RRC connection and requires no specific configuration, and can therefore be used at any time. The logical channel used in this case is the common control channel. During RRC connection establishment signaling, radio bearer number 1 is set up and will therefore be used for all RRC messages. When signaling radio bearer number 2 is later established, it will be used for all RRC messages carrying NAS messages. Signaling radio bearer number 2 has a lower priority than signaling radio bearer number 1. System information messages are of importance for UEs in both RRC idle and RRC connected states. All system information messages are delivered on the logical channel broadcast control channel. The system information is organized into different types of information blocks, depending on the type of information and its importance. The Master Information Block, MIB, includes information required to be able to read the rest of the system information: downlink bandwidth, configuration of the physical HARC indicator channel, and system frame number. MIB is delivered on the transport channel BCH, broadcast channel, and further on the physical broadcast channel. Other system information is included in System Information Blocks 1 to 11, where only SIB1 is a message on its own. All the other SIBs will be grouped together, as required, into System Information Messages, SI. SIB1 and SI are delivered on the downlink shared channel on the physical downlink shared channel. Another important task for the RRC is to control the measurement configuration and evaluation measurement results in order to make decisions about, for example, handover. The RRC in eNode B will send information about measurement configuration to the RRC in the UE. This will be included in the RRC connection reconfiguration message. The RRC layer in the UE will inform the physical layer about the required configuration and acknowledge the reception of the measurement configuration by sending the RRC connection reconfiguration complete message to the RRC in the eNode B. The physical layer will perform measurements as ordered, and when triggered, measurement results will be delivered from the physical layer to the RRC in the UE. The RRC in the UE will generate a measurement report including these results and transmit them to the eNode B. The RRC in the eNode B will evaluate the measurement results and then possibly make a handover decision. RRC messages includes information about message type. In this document, message types are marked in black with bold text. In the message, information elements are added, marked in black with plain text. But in RRC, information elements can be added into another information element as Russian dolls. IEs in IEs in IEs. In this document, the first level of information element carrying another IE will be marked in blue and will be underlined. By clicking on the blue underlined text, a detailed description of the IEs on the first level will be reached. The second level of IEs is marked in red and underlined. By clicking on the red underlined text, a detailed description of the IEs on the second level will be reached. The third and last level of IEs is marked in green and is underlined. By clicking on the green underlined text, a detailed description of the IEs on the third level will be reached. The RRC is responsible for providing the UEs with information about the radio network through system information. System information is of importance for the UEs in both RRC idle and RRC connected states. All system information messages are delivered on the logical channel broadcast control channel. The master information block, MIB, is delivered on the transport channel, BCH, broadcast channel, and further on the physical broadcast channel. SIB1 and SI are delivered on the downlink shared channel on the physical downlink shared channel. The system information is organized into 3 types of messages, all delivered with a certain periodicity. MIB is delivered with periodicity of 40 milliseconds and with 3 repetitions within this period. The first transmission is sent in subframe 0 of a radio frame, for which the system frame number is a multiple of 4, and with repetitions in subframe 0 of other radio frames. As mentioned before, it includes downlink bandwidth, physical HARC indicator channel configuration, and system frame number. SIB1 is delivered with a periodicity of 80 milliseconds and with 3 repetitions during this period. The first transmission is sent in subframe 5 of a radio frame, for which the system frame number is a multiple of 8, and with repetitions in subframe 5 of radio frames, for which the system frame number is a multiple of 2. It includes information of importance for access, as well as information about scheduling of other SIBs. SIB1 includes PLMN ID, tracking area code, and cell identity, and in this example, it also includes scheduling, information for system information 1 and 2. SI1 will have a periodicity of 160 milliseconds and include SIB3. SI2 will have a periodicity of 320 milliseconds and include SIB4 and SIB5. System information SI. As mentioned, the scheduling information for SI messages are provided in SIB1. The periodicity can be set to an interval between 80 and 5120 milliseconds as required. Here, SI1 is shown. Apart from including SIB3, as indicated in SIB1, it also includes SIB2. SIB2 is always the first SIB included in the first SI. The different SIBs that are delivered in SI are today: SIB2, carrying information about common and shared channels, for example uplink bandwidth and PRAC configuration. SIB3, with common information about cell reselection. SIB4, with information about neighbors for inter-frequency cell reselection. SIB5, with information about neighbors for inter-frequency cell reselection. SIB6, with information about neighbors for cell reselection to UTRA. SIB7, with information about neighbors for cell reselection to GRAN. SIB8, with information about neighbors for cell reselection to CDMA 2000. SIB9, including information about home eNode B. SIB 10 and 11, used for earthquake and tsunami warnings. This picture illustrates the timing of the system information. MIB has 40 millisecond repetition time and is always delivered in subframe number 0. The first transmission is here delivered in radio frame, with the system frame number equal to 12. 12 modulo 4 equals 0. In the following 3 radio frames, MIB is repeated. The next MIB has its first transmission in radio frame number 16, and so on. SIB1 has 80 millisecond repetition time and is transmitted in subframe number 5. First transmission is in radio frame with system frame number 16. 16 modulo 8 equals 0, and is thereafter repeated 3 times in every second radio frame. SI messages are dynamically scheduled to occur within specified SI windows of certain length, valid for all SI messages, and periodicity as specified per SI message. SI windows for 2 or more SI messages will never overlap. In this example, there are 2 SI messages, SI1 and SI2. The length of the SI window is here 2 milliseconds, which equals 2 subframes, and the periodicity for SI1 is 8 radio frames, and for SI2 it is 16 radio frames. The SI window can vary between 1 up to 40 milliseconds. The position, i.e. subframe number and system frame number of radio frame of the SI window for SI1 and SI2 are calculated using the formulas shown. Here the SI window for SI1 is shown in dark green, and for SI2 in light green. Whenever system information changes, the UE will be notified through paging. A system information value tag included in SIB1 is changed whenever any of the SIBs 1 to 9 are changed. Hence, a UE will be able to see whether there has been any changes of system information since it was last decoded. The system information will only be changed within specified modification periods, and information about the start and length of a modification period is included in SIB2. For ETWS notification, SIB10 and SIB11, changes can occur at any time and are indicated through paging. The modification period can have a value in the range from 64 up to 4096 radio frames, parameter M. The modification period will start in a radio frame for which system frame number modulo M equals 0. In this example, M is equal to 64, and this means that modification periods will start at radio frame with system frame number equal to 0, 64, 128, and so on. During one modification period, a paging message delivered on PCH on physical downlink shared channel indicates a change in system information.
The change will not take place during the current modification period, but at the beginning of the next period. Master information block. System information is not delivered on any defined signaling radio bearer. RLC transparent mode is used and the logical channel is the broadcast control channel. For MIB, the transport channel used is the broadcast channel and the physical channel is the physical broadcast channel. MIB includes information about downlink bandwidth in number of physical resource blocks, PHIC configuration and system frame number. PHIC duration gives the number of OFDM symbols on which PHIC will be mapped, and from PHIC resource the number of PHIC groups will be calculated. The system frame number consists of 10 bits and is used to identify radio frames to, for example, provide scheduling information. System Information Block 1. System information is not delivered on any defined signaling radio bearers. RLC transparent mode is used and the logical channel is the broadcast control channel. For SIB1 and system information messages, the transport channel used is the downlink shared channel and the physical channel is the physical downlink shared channel. SIB1 includes cell access related information such as PMLN identity for up to 6 different PLMNs, together with information if this specified cell for this PLMN is reserved for operator use or not. Tracking area code and cell identity. SIB1 also includes scheduling information such as SI window and for each system information message which SIBs are included, and the periodicity. Important information is also scheduling and contents information for the system information messages. There can be a maximum of 32 system information messages, each scheduled with a periodicity in the range from 8 up to 512 radio frames, and the contents can be any combination of SIB3 to SIB11. Note that SIB2 is always included in System Information Message 1. SI window length can be set between 1 and 40 milliseconds and is valid for all system information messages. Finally, the system information value tag, value between 0 and 31, is increased by 1 when any information in SIB1 to SIB9 has been updated. System information message. Regarding system information, there are 3 types of messages: MIB, SIB1, and system information message. There can be up to 32 different system information messages. Each system information message is scheduled to occur with a chosen periodicity, including a number of SIBs, 3 to 11, as indicated in SIB1. Note that System Information Message 1 always includes SIB2. In this example, the System Information Message includes SIB2 and SIB3. Message structure of System Information Message. Connection control includes RRC connection control includes RRC connection establishment, at which the UE changes from being RRC idle to RRC connected, and signaling radio bearer 1 is established. The establishment is initiated by the UE, but can be triggered by the network through a paging message. RRC connection release, a procedure initiated by EU-TRAN in order to order UEs to leave the RRC connected state and enter RRC idle state. Reasons for this could be that the UE is inactive for some time. Access stratum security is also part of connection control. It includes ciphering of information delivered on both signaling bearers and radio bearers, and also integrity check of RRC messages delivered over signaling radio bearers. RRC is responsible for configuration of security algorithms and the parameters key change indicator and next hop changing count used at handover or connection re-establishment. Mobility in connected mode is also an important task. For UEs in RRC connected state, EU-TRAN, the serving eNode B, makes the decision about handover. The UE moves closer to the cell border. As the UE moves closer to the cell border, the handover is triggered in the eNode B, which chooses a target eNode B. Once handover is triggered, the serving eNode B will send a RRC handover preparation message to the target eNode B. This message will include information about the resource required for the UE and the procedures referred to as prepare target cell. Once a positive response is received, the UE will be ordered to do a handover. The UE will attach the target eNode B. Once the handover is successfully completed, the new eNode B will be the serving eNode B. Paging is used in order to inform RRC idle UEs about incoming services, and also to inform UEs in either RRC idle or RRC connected states about a change in system information. The paging message is not delivered on any defined signaling radio bearer. RLC transparent mode is used, and the logical channel is the paging control channel. The transport channel used is the paging channel, and the physical channel is the physical downlink shared channel. The paging message includes a list of identities together with information about if the page origins from the packet switched or the circuit switched network for each UE being paged, max 16. The identity used could either be STIMC or IMC. If the system information modification element is included, it indicates that at least one of the SIB 1 to SIB 9 is updated. If the earthquake and tsunami warning indication is included, it indicates an earthquake or tsunami notification, i.e. that SIB 10 and or SIB 11 is to be found in the system information. The RRC connection establishment procedure involves exchange of 3 RRC messages. Through this procedure, the UE will change from RRC idle to RRC connected state, and the signaling radio bearer 1 will be established. The establishment procedure is initiated with the RRC connection request message sent from the UE to the eNode B. This message is delivered on signaling radio bearer 0. RLC transparent mode is used, and the logical channel is the common control channel. The transport channel used is the uplink shared channel, and the physical channel is the physical uplink shared channel. The content of this message includes the UE identity, which is either the STIMC if current cell belongs to the same tracking area as the UE was previously connected to, or else a random number of 40 bits, and the cause for performing the RRC connection establishment procedure. eNode B will respond with the RRC connection setup message. Also, this message is delivered on signaling radio bearer 0. RLC transparent mode is used, and the logical channel is the common control channel. The transport channel used is the downlink shared channel, and the physical channel is the physical downlink shared channel. It includes a RRC transaction identifier together with a major settings for dedicated radio bearers, MAC, and physical layer. From now on, the UE will be RRC connected, and signaling radio bearer 1 will be used for all RRC messages until a signaling radio bearer 2 is established. The UE will finish the procedure through sending the RRC connection setup complete message. This message is delivered on signaling radio bearer 1. RLC acknowledge mode is used, and the logical channel is the dedicated control channel. The transport channel used is the uplink shared channel, and the physical channel is the physical uplink shared channel. The content will consist of a RRC transaction identifier with the same value as received in the RRC connection setup message, identity of the PLMN selected, identity of MME in which the UE is registered, if any, and finally a NAS message as required. Message structure of RRC connection setup. Initial security activation procedure is initiated by eNode B to activate the access stratum security at RRC connection establishment. The access stratum security must be activated before signaling radio bearer 2 is established. The security mode command is sent from eNode B to the UE. It is delivered on signaling radio bearer 1. RLC acknowledge mode is used, and the logical channel is the dedicated control channel. The transport channel used is the downlink shared channel, and the physical channel is the physical downlink shared channel. The message includes an RRC transaction identity together with information about which ciphering or encryption and integrity algorithms to use.
When the UE receives the security mode command message, it shall derive the keys needed for radio bearer ciphering or encryption and for signaling radio bearer ciphering or encryption and for integrity check. Request the lower layers PDCP to perform an integrity check on the received security mode command message using the selected integrity algorithm. If it is OK, it shall request the lower layers PDCP to perform integrity protection on every RRC message sent UL from now on, and to perform ciphering on all UL signaling and user data following the security mode complete message. The UE will send the security mode complete message, note with integrity protection but no ciphering. It is delivered on signaling radio bearer 1. RLC acknowledge mode is used and the logical channel is the dedicated control channel. The transport channel used is the downlink shared channel, and the physical channel is the physical downlink shared channel. It only includes the RRC transaction ID, same value as in received security mode command. From now on, AS security is activated. The RRC connection reconfiguration procedure is the one with most usage. It is used to modify an existing RRC connection for a number of reasons: to add or remove or modify a radio bearer for either signaling or data, to handle handover, and to modify measurement configuration. The RRC connection reconfiguration message is sent from eNode B to the UE. It is delivered on signaling radio bearer 1. RLC acknowledge mode is used, and the logical channel is the dedicated control channel. The transport channel used is the downlink shared channel, and the physical channel is the physical downlink shared channel. The content of the message will depend on how the RRC connection shall be modified. It will always include an RRC transaction identity. If modification relates to measurement control, the information element mes_config will be included. If sent for handover purposes, the information element mobility control info is always included. If a NAS message is included, it will be carried in the information element dedicated info NAS list. Note, it is never included in case of handover.
Information about configuration of dedicated resources is carried in the information element radio resource config dedicated. This information element is always included at handover to EUTRA, else it is conditional.
To transfer information about security parameters during handover, the information element security config handover is included. As a successful response to this message, the UE will send the RRC connection reconfiguration complete message. It is also delivered on signaling radio bearer 1. RLC acknowledge mode is used, and the logical channel is the dedicated control channel. The transport channel used is the uplink shared channel, and the physical channel is the physical uplink shared channel. The content is only the RRC transaction identifier.
Message structure of RRC connection reconfiguration. The RRC connection reestablishment procedure is used to re-establish an RRC connection in, for example, the case of unsuccessful handover. It involves reactivation of signaling radio bearer 1 and security. It is only possible to make a successful re-establishment to an eNode B with a valid UE context. The UE will initiate the re-establishment procedure by sending the RRC connection re-establishment request message. This message is sent on signaling radio bearer 0. All other radio bearers have been suspended. The message is sent on the same resources as the RRC connection request message. The content of the message is a UE identity consisting of CRNTI, physical cell ID, and a short MAC I, together with a re-establishment cause, such as handover failure or other types of failure. In response to this message, the eNode B will send the RRC connection re-establishment message, also on signaling radio bearer 0 on common control channel. This message contains a RRC transaction ID, the radio resource config dedicated information element, and the parameter next hop changing count. In case of successful re-establishment, the UE will respond with the RRC connection re-establishment complete message, sent on the now reactivated signaling radio bearer 1. The message will also be both ciphered and integrity protected, using the reactivated and updated security keys. The message includes only the RRC transaction identifier. The RRC connection release procedure is initiated by eNode B in order to release the RRC connection, including the release of all radio bearers and radio resources. The message is sent, as most RRC messages, on signaling radio bearer 1 on dedicated control channel. It includes RRC transaction identifier, a release cause, and possibly redirected carrier information and/or idle mode mobility control information. Once the UE has received this message, it will change to be RRC idle. The procedure for handover within EU-TRAN will depend on whether the handover involves a change of serving gateway or not, as well as if the X2 interface is available or not. The intra-EU-TRAN handover involves the usage of internode RRC messages. Internode messages are used to transfer RRC messages between eNode Bs and/or UEs via other interfaces than the radio interface. The two internode messages involved in the handover are the handover preparation information and the handover command. In this example, the handover is carried out between two eNode Bs, between which the X2 interface is implemented, and there is no change of serving gateway or MME. The handover is triggered in the serving eNode B, which selects a target eNode B. The serving eNode B will send a X2 AP message, handover request to the target eNode B. This message will include the internode RRC message handover preparation information message sent to prepare target eNode B for the handover. This message includes information about UE capabilities, configuration of access stratum, radio resource management configuration, and access stratum context. In response to the HO request, the target eNode B will respond with the X2 AP handover acknowledge message, including the internode RRC message handover command. This message will include the RRC connection reconfiguration message, which will be delivered to the UE via the serving eNode B. This RRC reconfiguration message will as a minimum include the information elements, mobility control info, and security config handover info. When receiving this message, the UE will perform random access towards the target cell, either using dedicated random access preamble or using contention-based random access. Once random access has been successfully performed, the UE will send the RRC connection reconfiguration complete message to the target eNode B, which from now on will be the serving eNode B. In this example, the handover is carried out between two eNode Bs, between which the X2 interface is not implemented. There is no change of serving gateway or MME. The handover is triggered in the serving eNode B, which selects a target eNode B. The serving eNode B will send a S1 AP message, handover required to the MME. This message will include the internode RRC message, handover preparation message, aim for target eNode B. The MME will send the S1 AP message, HO request, to the target eNode B, in which the handover preparation information message is forwarded. In response to the handover request, the target eNode B will respond with the S1 AP handover request acknowledge message, including the internode RRC message handover command. The MME will respond the handover required message with the S1 AP handover command message, in which the internode RRC message handover command is forwarded. This message will include the RRC connection reconfiguration message, which will be delivered to the UE via the serving eNode B. When receiving this message, the UE will perform random access towards the target cell. Once random access has been successfully performed, the UE will send the RRC connection reconfiguration complete message to the target eNode B, which from now on will be the serving eNode B. In this example, the handover is from a UTRA Node B to a eUTRA eNode B for PS service. The handover is triggered in the serving RNC, which selects a target eNode B. The serving RNC will send a RANIP relocation required message to SGSN, including the internode RRC handover preparation message, which is aimed for target eNode B. This message will be forwarded from SGSN to MME in the forward relocation request message. and then from the MME to the target eNode B in the handover request message. The eNode B will respond with the handover request acknowledge message, including the internode RRC handover command message, carrying the RRC connection reconfiguration message, which will be transparently delivered to the UE via MME SGSN serving RNC and Node B. When receiving this message, the UE will perform random access towards the target EUTRAN cell. Once random access has been successfully performed, the UE will send the RRC connection reconfiguration complete message to the target eNode B, which from now on will be the serving eNode B. In this example, the handover is from a EUTRA eNode B to a UTRA Node B for PS service. The handover is triggered in the serving eNode B, which selects a target Node B. The serving eNode B will send a S1AP handover required message to MME, including the source RNC to the target RNC transparent container, which is aimed for target RNC. This message is encoded according to target RAT standard, here UTRA. The message will be forwarded from MME to SGSN, then to the target RNC. The RNC will respond with the relocation request acknowledge message, including the target RNC to source RNC transparent container, which will be transparently delivered to the UE via SGSN, MME, and source eNode B. When receiving this message, the UE will perform random access towards the target UTRA cell. Once random access has been successfully performed, the UE will send the HO to UTRAN complete message to the target RNC, which from now on will be the serving RNC. There are different types of measurements. Intra-frequency, meaning measurements on the same downlink frequency as is used in the serving cell. Inter-frequency, measurements made on frequencies other than that used in serving cell. And inter-RAT frequencies, measurements on UTRA, YRAN, or CDMA frequencies. The UE will be informed about the measurement configuration through the RRC connection reconfiguration message, including the MES config information element. Here, the list of measurement objects, reporting configuration, and measurement identities are included. Parameters used to configure measurements are, for example, measurement objects, identified by MES object ID. For intra or inter-frequency measurement, the measurement object is a single EUTRA carrier frequency with associated list of cells. For inter-RAT UTRA or CDMA measurements, the measurement object is a set of cells on a single carrier frequency. For inter-RAT YRAN, the measurement object is a set of YRAN frequencies. Reporting configuration. identified by report config ID. Reporting criterion, type of event and quantity that shall trigger the reporting. There are a number of defined trigger events. For EU-TRA, events A1 to A5, and for Inter-RAT, events B1 and B2. Trigger quantity is either reference signal received power or reference signal received quality. Reporting format, indicating what shall be included in the report, such as type of result to report RSRP or RSRQ and number of cells to include. Measurement identities, identified by MES ID, used to configure different measurements through combinations of measurement object and reporting configuration.
A measurement report will be generated when triggered by occurrence of an event, as described in the report configuration. The RRC message, measurement report, is sent from UE to eNode B on signaling radio bearer 1. It includes MES ID for the measurement that was triggered together with the actual measurement result for both serving cell and neighboring cells. Same and or different RAT. The result provided could be reference signal received power, RSRP, and or reference signal received quality, RSRQ.
Here is an example for measurement configuration. Green color indicates the serving cell, EU-TRA. Blue color indicates EU-TRA. And red color indicates U-TRA. 3 measurement objects are defined. MES object ID 01 for EU-TRA measurement, cell W and cell X. MES object ID 02 for UTRA frequencies 1, cell Y. MES object ID 03 for UTRA frequencies 2, cell Z. 3 reporting configurations are defined. Report config ID R1, indicating the reporting shall be triggered by event A1, serving cell better than threshold with at least the hysteresis value. Report config ID R2. Reporting is triggered by event A5, serving worse than threshold 1 and neighbor better than threshold 2. Report config ID R3. Reporting is triggered by event B1, inter-RAT neighbor better than threshold. 4 measurements are then defined, with the following measurement identities with the listed combinations of measurement object and report configurations. MES ID M1, combining MES object ID 01 with report config ID R1. MES ID M2, combining 01 and R2. MES ID M3, combining 02 and R3. MES ID M4, combining 03 and R3. In the example previously introduced, the measurement report for MES ID M2 is triggered. MES ID M2 combines MES object ID 01 and report config ID R2. For R2 event A5 triggered the reporting. Event A5 means serving cell frequency worse than threshold 1 plus the hysteresis value, and neighbor cell frequency is better than T2 plus H. Hence, the measurement report generated will be indicating that the report is for MES ID 2 and include measurement results for serving cell and the neighboring EU-TRA cells listed, W and X.
The RRC procedures that are only used to transfer NAS messages UL and DL are the DL information transfer and the UL information transfer. If signaling radio bearer 2 has been established, both the UL and DL information transfer messages will be delivered on that, else on signaling radio bearer 1. RLC acknowledge mode is used. The DL information transfer message includes an RRC transaction identifier together with the NAS message. By default, an RRC transaction identifier shall be included in all DL RRC messages on signaling radio bearer 1 and 2. The UL information transfer message only includes the NAS message. For UL RRC messages that are not a response to a DL RRC message, which is the case here, the RRC transaction identifier is not included. This RRC traffic case gives an idea on how the messages belonging to different RRC procedures are used together. The main steps included in the RRC connection establishment combined with an attach is shown. In those cases when the RRC message includes a NAS message, the name of the NAS message or NAS messages is also included. NAS messages in blue text are an EPS mobility management message, and a NAS message in green text is a EPS session management message. The blue arrow to the right is just a reminder that all the NAS messages are transferred also between eNode B and MME.